This is Mr. Potter. We're going to continue talking about finding antiderivatives by substitution. And as I mentioned in yesterday's lesson, the best way to go about learning this technique is practicing. You have to continue practicing. And being exposed to different problems so you can understand the tricks that are used to make these look like relatively simple antiderivatives. That exposure to that practice is really the only way that that a student can really get better at this. So what I want to do is I want to actually go through 4 examples of antiderivatives by substitution. So the first one I'm going to do is this integral of 4 secant squared 4x tan 4x dx. And so my first instinct is, because we were talking about composition of functions in yesterday's lesson, I noticed that I've got a composition of functions here. I've got this something squared, and the something that's being squared is secant of 4x. I mean, this is really the secant of 4x that's being squared. And so if I let u be the secant of 4x and try and go from here, I notice something rather interesting. I know that the derivative of secant is going to be secant of theta times tan of theta. So my du in this case ends up being secant to the 4th x tangent to the 4th x times the derivative of theta, which in this case is 4 dx. So this is my du, and I notice that although my original intent was to get secant squared, I ended up only needing one secant in there because the other secant is actually incorporated in my du. This integral actually can be rewritten as the integral of secant 4x times secant 4x tan 4x times 4 dx. Because every part I can find in this differential. So what I end up with doing my u-substitution, if I let u be secant of 4x and du being secant 4x tan 4x times 4 dx, this actually becomes the integral of u du. And this form confuses a lot of people. But what's really happening is this is really u to the first power. And so if I'm taking the antiderivative of a variable to the first power, I'm just going to use our power rule. I'm going to increase the exponent by 1, and then divide by my new exponent. So I get u squared over 2 plus a constant. So this is really the secant of 4x that's being squared divided by 2 plus a constant. Now, this is one way that I could have approached it, but there is a completely different way that's perfectly legitimate to look at. If instead of looking at this secant squared, if I thought to myself, I know that the derivative of tangent is secant squared. So if I let u be tangent of 4x, then my du would be the derivative of tan 4x, which would be secant squared 4x times 4 dx. And so I notice that here's my u, and here's du. Du is completely included in that as well. So this becomes the integral of tan 4x times secant squared 4x times 4 dx. So I've got, again, the integral of u du. And this gives me a little bit perplexed because I'm looking at this and I'm going, wait a minute, well, this is u to the first. That same power rule that we talked about would give me u to the second power over 2 plus c. But u in this case is tangent. So this is really the tangent of 4x that's being squared divided by 2 plus c. So the question is, how can my answer come out one way depending on one substitution of u, and a different way for a different substitution of u, and yet be the same thing? And the reason that's true is because of this trig identity that we've mentioned on these videos before. I know that 1 plus the tangent squared of theta equals the secant squared of theta. And so for this very reason, I could say that 1 plus the tangent squared of 4x would be equal to the secant squared of 4x. In other words, these two terms, tangent squared of 4x and secant squared of 4x, differ by 1. And this 1 could be explained as these having different constants, these constants differing by a value of 1. In other words, C1 is really C2 plus 1. So I just want to mention this, the idea that because of the trig identities that we've learned in our pre-calculus class, we could take two completely different approaches. One approach using one value for u, one approach using a different value of u, end up with functions that look completely different and yet end up being equal, only being different by a constant. So I wanted to go through this example. I also wanted to say that you're not always going to use trig identities to simplify an expression. And so in our next example, I want to take a look at this. I've got the integral of sine squared 2x times cosine 2x dx. So what I'm going to do is I'm going to go through our traditional way of approaching this problem. If I let u be sine of 2x, because I'm looking at this as a composition of functions, it's really sine of 2x that's being squared. Then du in this case would be equal to the cosine of 2x times 2 dx. And I have the cosine of 2x, I have the dx, I just don't have this 2. So I know that the cosine of 2x times dx is really equal to 1/2 du. And so this problem becomes the integral of u squared times 1/2 du. And this is something that I can take the antiderivative of using the power rule. So this ends up being u cubed over 3, and this constant is really just a 1/2 coefficient plus c. So I end up with u cubed over 6 plus a constant, or the sine of x cubed over 6 plus a constant. But if I try and be clever and I say, oh, well, I know that sine squared of theta plus cosine of squared theta equals 1, then I can rewrite sine squared theta as being 1 minus the cosine squared theta. And so I can rewrite this integral as being the indefinite integral of 1 minus cosine squared theta times cosine 2x dx, where theta in this case is the 2x that I'm dealing with. Then perhaps I can find the antiderivative this way. I don't have to look for a u and a du because everything's in terms of cosine. And I can distribute. I can let this be cosine of 2x minus cosine cubed of 2x. That's all being multiplied by dx. And one of the properties that we had with derivatives is if I had a polynomial or if I had the sum or difference of terms, the sum of the derivatives were the derivative of the sums. And that same property holds for antiderivatives. So I could find the antiderivative of each of these two functions separately and then just subtract the results. And in this case, if I let u be 2x, then du would be 2 dx. But all I have is just 1 dx. So I end up with 1/2 du. And I know that the antiderivative of cosine is sine, so that this ends up being sine of 2x times 1/2 plus a constant, which I can take care of at the end. But over here, this is a little bit more troublesome. If I take a look at this and say, oh, it's a composition of functions, it's something cubed. If I let u be the cosine of 2x, then du would be the negative sine of 2x. And nope, that's not going to help me because I don't see sine. So if I let u be 2x and du in this case being 2 dx, I still have cosine cubed of u, which isn't going to help me at all. So because this isn't going to help me at all, I have no idea how to approach this part over here. And so I noticed that just going this standard way is probably going to be the best way. So there are some times when trig identities are beneficial, and there are some times when trig identities are just going to lead to more confusion. So I wanted to go through an example, one where a trig identity was beneficial, and one where a trig identity actually ends up leading us down a rabbit hole. I wanted to go through a couple more examples here. Keeping in this vein of antiderivatives, I've got the antiderivative of 1 over x ln x. And we've talked about how when I see a fraction, I often want to look at the denominator. The issue here is if I think of this as being the integral of x times ln x to the negative 1, this is going to still be pretty complicated. If I let u be x times ln x, then my derivative, I end up having to use a product rule. And when we go to section 6.3, we'll talk about how do we deal with product rules, but this is not the method to deal with it. Here, du ends up being x times 1 over x plus the natural log of x times 1 dx. I get something that's ugly. So this is not going to work. What I want to do instead is I want to think of this as being 1 over x times 1 over natural log x dx. And this is my more complicated part. This is the part where I want to look for u. This is simpler. And so this is probably going to be part of my du. So if I let u be natural log of x, then du, the derivative of natural log, is 1 over x dx. And so I end up with 1 over u times du. And I know the antiderivative of 1 over u is the natural log of the absolute value of u plus c. And u in this case is natural log x. So I actually end up with the natural log of the absolute value of the natural log of x plus c. And as I mentioned before, you can always check by taking the derivative of the function that we end up with. So if I have natural log of natural log x plus a constant, and I want to take its derivative, I know the derivative of a constant is 0, but I know that the derivative of natural log of blah would be 1 over my blah times the derivative of blah. And I notice that this looks an awful lot like what I started off with at the beginning. So this is something that we'll see a lot with natural log. I can see a lot of different integrals involving natural log. I might see something like the natural log of x cubed over x dx, or I might see the integral of 1 over x times the natural log of x squared dx. I could see a lot of these formats where rewriting it as 1 over x times natural log of x to some power is going to make it an easier integral to work with. So just wanted to make sure that everyone's aware that this is a technique that we have. This u-substitution helps us deal with finding the antiderivative of natural log with 1 over x with it. And the last example that I want to go over today is dealing with something that seems pretty straightforward. The integral of cotangent of x. So if I want to find the antiderivative of cotangent, I'm kind of lost here because looking at this, I remember that I should see a composition of functions. I should see f of g of x involved somewhere in here because I'm looking to undo the pro the chain rule. I'm really looking to undo this chain rule. So I'm looking for the product of two functions, one which is a composition of functions, and this is how I find u. And the other part is something that kind of alludes to the derivative of u, usually just being off by a constant. But I've got cotangent, and cotangent, well, it just seems real simple, which is one of those situations where having a simple function makes it more difficult to work with. But if I was to rewrite this as the integral of cosine of x over sine x dx, rewriting it like this, I can see that I've got this denominator here. So this is really cosine of x times sine of x to the negative 1. And now I see there's my composition of functions. So if I let u be sine of x, du in this case would be cosine of x dx. And so what I've got is the integral of u to the negative 1 du, which is natural log of u plus a constant, or the natural log of sine x plus a constant. And I can use this technique to deal with the integral of cosine, or similarly, I could talk about the integral of tangent x, because I could rewrite this as sine x over cosine x dx, and approach it in that same way. So I just wanted to bring to mind some of these examples that we can see where I have a problem that kind of looks hopeless or looks impossible. Those problems where it's very difficult to find a place where exactly I'm supposed to start. And we can get a grasp on it using the substitution. We can find a way to write it as a composition of functions, determining our u, finding our differential du, and writing it so that the integral is much simpler. So this is Mr. Potter. Thank you for watching. Have a great day.